Hi, so in this video we're going to look at some of the graphs we were doing in the last video, but in Geogebra. So if you ever wanted to get a good idea of what's going on, you can always try to look at Geogebra and try to take a look-see. So we're going to orient it. This is the way we're usually looking at it. As you saw in the last video, this might be a more productive kind of view of things sometimes, just so we can maybe get a better idea of certain shapes. We'll see what we have to do. Red is X, green is Y, blue is Z. So if I'm trying to graph something like R of t, square root t, comma, 1 over, this was the first one we did, t minus 1, comma, natural log of t. And so what we see here is this weird kind of shape. And for that domain, we're getting a curve that's floating in space in a weird way. So that's why I would say we would never try to draw this by hand, but that's what it looks like. And it might not even look like a curve when you're first looking at it. It might be like, oh, I guess it's just living on the x-axis. No, it's definitely having some, sorry, the xy plane. It's definitely having some lift. I'm not going to spend time graphing all of the ones we saw, but we can look at what happens if I start to adjust this to our second example, where we had a much more restrictive domain. So that was natural log of 3 minus t, and root t at the end. I notice that when I'm trying to type in square root, okay, I just typed in 3 minus t, square root sqrt. That's all you have to do. And here you see the restrictive domain has given us a firm starting point, and it actually gives us a kind of weird ending point as well. We really can't get past that limit at 3. We have a big issue if we try to go past 3. But 3 is happening at a y coordinate of infinity, so it's going to look like it's going on forever. Okay, a y coordinate of negative infinity, I'm sorry. Okay. All right, so if I'm trying to look for 2 components, I'm going to have to rename it as r of t equals, so we put parentheses, square root t, this was our second example, comma, 4 minus t. We notice that this is a plane curve. It's only living on the xy plane, and it's that half parabola we described. If I decide to change things up, like I tell GeoGebra it's a 0 comma, what should happen? We now have a plane curve that's living on the YZ plane only. It doesn't travel at all in the x direction because the x direction's locked in at 0. And this is what I was talking about. If we only have those 2 components, it's going to live on that plane. Then we looked at a line, and our line was a rather poor drawing, perhaps, but I had something like 1 plus t, comma, 2 minus t, comma, 3 minus 2t. It doesn't look that much worse than my line, or much better, I guess. But here we can spin things around and see, okay, I can see now it does have 3D components. It's not just a line in the YZ direction. It's not just a line in the XZ direction. It's a line in all 3 directions. And remember, for us, the parameterization is giving us an orientation. There is a sense which we're at here-ish before we're at here. I want to show you the twisted cubic. Let's see what happens if I don't try to name it. T comma t squared. So what's that look like? A parabola, a plane curve. And then we give it one more directionality to it. Bam. Okay, so that's for positive and negative t. but we can see it's twisting around. This is why it's a twisted cubic. It's not just a cubic, it's clearly moving along something. And that's why the surface might be good for us to see. And what surface did we decide this was living on? It was living on the surface y equals x squared. And this can reveal to us something a lot more clear about the path of that particle. It's much nicer to be able to describe, oh, I see it now. Speaking from my own experience, I did not understand that that was the point of how it was a twisted cubic. I didn't understand it was traveling along the surface until I took a much more close look at things for one of the years I taught this class. And I think my second drawing was pretty good for this. That first drawing is kind of rough because I guess I was looking at this kind of angle, which is really hard to draw accurately. Like, I don't even like how Geogebra renders it, blah. Okay, so that's my twisted cubic. Okay, then we had something like it was traveling along a elliptic cylinder. I can show you, we have 2 cosine t, 4 sine t in the y direction. So yeah, that makes an ellipse. And that's why when we just fix 3, it just lifts up that onto a point in 3D space. And it's just floating there like a halo. And if it's distorted looking, it's because of the axes. But actually, I think our axes are actually pretty in sync. I don't know. And we can see it's on the cylinder that you would get if you had, it was something like x squared. Sorry, it would be 4x squared plus y squared equals 16. And we can see it's like a belt on that cylinder. And this is not what we drew, but if I start changing this last component to 2 or to t, we start getting somebody who's floating there, spiraling around that cylinder. That's what we would call a helix. Okay, it's spiraling around, going up and up and up. And I think it looks nice if we spin it sometimes. Like it can look mesmerizing. Once we start changing things, like giving these two if we start changing how these two components act in terms of their coefficients, that's where we start getting things like, sorry, it's giving me a hard time. Okay. A much more careful spiral. And now we can see, this is what I was trying to say in the video, we're getting further from this z-axis as we go up. In the other spiral, in a helix shape, so the helix shape, just for reference, we can maybe compare the two. The helix shape is cosine t, sine t, t. I'm going to give it a different color settings. Okay, no, setting. This guy's settings. Color, there we go. I don't know why it was. All right, so in red is my helix, like what a true helix looks like. Red is completely defined by our typical cylinder, our unit cylinder like this, okay? Red is bounded. It always will be 1 unit away from the z-axis, whereas black is on the cone, and the equation of the cone was z squared equals x squared plus y squared. I do want a different color there, huh? So this guy has to wait. Really? Okay, thank you so much. I don't know why. Sometimes it's easy, sometimes it's hard, right? So Christmas colors, I guess, red and green, but we can see that, again, our second helix, once I have these other coefficients, t cosine t, t sine t. Now we're getting further and further, and we're traveling along the cone. Another type of curve we might be interested in is the curve that would be the intersection of two kinds of surfaces. So if I get rid of this helix and I'm looking at my unit cylinder, there he is, and we try to chop it with a plane like 2x plus 3y plus z equals 2, 1, 2. I don't know. Doesn't matter. We can see that this is slicing through the cylinder at a interesting kind of angle. And what this will create, if we look at the intersection of these two, intersect two surfaces. So I'm just going to click on the blue plane, and we're going to try to click on the red cylinder. And I'll shut them both off. We can see what we create was what is really an ellipse, but it's an ellipse that's living on this secondary plane. And the book shows you how to come up with things like that, but I'm just saying in terms of graphing it, I'm not really interested in graphing too much like this. I'm mostly interested, do you understand that this is a path that's living on both the plane and the unit cylinder, right? And that's all I have for this video. Thanks for watching. Feel free to play around with it, especially when you're doing your homework, to try to get an idea of what these things look like in 3D space. Hope you learned something new. I'll see you in the next video. Thanks.